Hi. So in today's video, I will discuss about SPWM inverter, or you can say sinusoidal pulse width modulation inverter. So, what is inverter? Inverter is a circuit or a topology that can convert DC voltages into an AC voltages. So we can use a DC voltage to run our AC loads. So first, what is SPWM inverter? In SPWM inverter, we have a sinusoidal component of frequency, let's suppose 50 hertz or 60 hertz, and then we have a carrier frequency of about 5 kilohertz, 2 kilohertz. That depends on your choice. So here in this picture you can clearly see that we have a reference voltage of sinusoidal, that is Vref, having a frequency of, let's suppose, 50 hertz, and we have another signal that is of triangular waveform which have high frequency, let's suppose 5 kilohertz. So we will compare these two signals using a comparator. You can make the comparator using an operational amplifier. So we will do the simulation in the MATLAB, and we will compare both the reference voltage and the carrier wave, and we will see that the signals will be of SPWM type, which means the duty of the pulses will be changed, or as the magnitude of sine voltage changes or increases, then the duty of the PWM signal will increase. I will show you it in the simulation, and then we will use an edge bridge which will convert our DC voltages to into an AC voltages. So coming towards the simulation, I will show you all these graphs and output graphs. So coming to the MATLAB file, I have simulated circuit in the Matlab Simulink. So here we have a triangular wave which have a frequency of 5 kilohertz, and I have another signal that is sinusoidal wave function having an amplitude of 1. The amplitude of this triangular wave is also 1 volt, and we have selected the frequency as 314.2 radian per second, and you can convert it into in hertz, that is 50 hertz. So by comparing these two signals using a comparator here or relational operator here in MATLAB, so practically you will compare both these signals using comparator and using operational amplifier. So first I will show you both these plots of that is, like if I show you the sinusoidal waveform, this is the triangular waveform of 1 volt plus minus 1 volt. I will zoom it to show you it clearly. Okay, so we have a triangular waveform that is of plus minus 1 volt, and we have another signal that is our that is of 50 hertz, or you can make it of 60 hertz. So we have both signals, our reference that is sinusoidal waveform, and we have a carrier signal that is triangular waveform. I have selected the frequency of carrier signal as 5 kilohertz, and the sinusoidal frequency is our main frequency or power frequency, that is 50 hertz. So by comparing both these curves or plots, we get the output waveform as like this one. I will show you it here, like you will clearly see that the duty cycle of the waveform or the output waveform that will go to the MOSFET gates is changing sinusoidally. So clearly you can see that when the sine amplitude is maximum, the duty of these pulses are maximum, and when we have low sine here, like if we have here the duty is very small and the duty is very high. So here the waveform, the sinusoidal, will be like this. Okay, so if I show you both the graphs, like I will first convert it into the 2 ports, and then will show you the output waveform and the sinusoidal waveform, and run the simulation to and here we will see that how the duty of the signal is changing according to the sinusoidal waveform. So first, by converting or by zooming this graph, we will see that, as you can clearly see, like I will zoom it more. So as the amplitude of sinusoidal waveform is maximum, we have a maximum duty cycle, and if here it will have a low duty cycle because the magnitude of the sinusoidal waveform is very low, so we have low duty here. Okay, so you there is another concept of like here the magnitude is 1 volt, and here the sinusoidal voltage magnitude is 1 volt. So if we increase or decrease the ratio of these voltages, we can also increase or decrease the duty of the output waveform. So I will discuss it later. So as we know that for the edge bridge to work, we have to apply the same signal here to MOSFET 2 and MOSFET 3, and same signal to MOSFET 1 and MOSFET 4. So I have given the signal to MOSFET 1 and in the same signal to MOSFET 4, and using inverter or NOT gate, I have given the signal to MOSFET 2 and MOSFET 3. And I have also connected a load that is of about 100 watt, and I have given a DC voltage of about 311 volt, which is the peak value of sinusoidal voltage. So running the simulation and by observing the output voltage, which is about plus minus 311 volt, and the output will be like SPWM. We will see it clearly that the magnitude here is large, and here it is in negative side it is large. So this output waveform is of square wave pulses, but it have components of 50 hertz. So using this technique, we can decrease the THD of the inverter, which is a good thing for us, because as we know that like if we design a simple square wave inverter, it will have a THD of about 50%. So it will generate more heat, and the efficiency of the inverter will be very small, and also it will generate heat in the inverter and in the load. And if we use this topology like SPWM based inverters, so we put a 50 hertz or 60 hertz signal in the pulses, and this pulses then appear in the output waveform, and we get the THD very low. And by using filter, low pass filter in the output, we can easily extract the sinusoidal waveform of about 220 volt RMS, or you can say 311 volt peak. So now I will show you the FFT analysis or fast Fourier transform analysis of this output waveform, and I will show you that the output waveform THD is very small. In this case, it will be about less than 10%, and also by using a very small filter, you can extract the pure sinusoidal waveform of this circuit. So coming to the FFT analysis of this circuit, again I will run the simulation here, and then I will use the FFT analysis tool using this Power UI block. So by double clicking this block and going to the tools and selecting FFT analysis. Okay, so here I have to discuss that how to connect this signal to the FFT tool. So by opening this scope, you will go to the setting and then logging, and you will log data to workspace, and you will give the name and save the format as dataset, and then you will save this information. So by going to FFT analysis in the tool option, you will see that our output is appearing here. So I have selected the fundamental frequency X 50 Hz, and this option is by default, and you can select number of cycles that depends on you. Like I will select, let's suppose 30 cycles, and you will select as same as maximum frequency option here, and by displaying we can see that the FFT analysis is here. Here we have a 60 Hz component, that is our 50 Hz component, that is our required component that will run our AC load, and these components are of no use, that can generate heat or some other effects. So we have a THD of about here 8.27%, which is very low by comparing it to the square wave inverter. So we have got our THD 8.2%, and you can extract a pure sinusoidal waveform from the output just by using a simple low pass filter, like a second order low pass filter, like connecting inductor and capacitor in low pass topology, and you can extract a pure sinusoidal waveform from here. So the importance or the significance of this inverter is that we can get sinusoidal output voltages, and we can run our loads smoothly. So this inverter is mainly used, or this inverter is coming the market, and we are getting pure sinusoidal waveform in the output. So the working principle is very easy. Like first I have generated the complementary waveforms for this MOSFET and these MOSFETs, and then just by running the edge bridge and connecting the outputs, we can get our output waveforms. So and the last thing is the THD. So the benefit of this inverter is that we can get a very low THD from this inverter, and which is of very it have very advantages in our loads. So thank you for watching.